Here in section 1.4, we bring chapter 1 to a close. In chapter 2, we will begin to talk about proof in a rather sort of roundabout way, I suppose, but that's ultimately what we're up to. Here we need to talk, in section 1.4, we need to talk about diagrams, what they can and cannot say. Perhaps a better way to put this is that diagrams speak a certain kind of language, and we have to make sure that we understand that language. It's very easy to make mistakes about the language that is spoken by diagrams. And these mistakes can often be fatal in the work that we do. And this is really quite famous. This is one complaint that's been made against geometry, really since geometry first began, is that the diagrams that it uses, the diagrams that are so incredibly useful, can mislead. And they can lead us to make assumptions that we have no right to make, and in certain instances, they can lead us to make assumptions that are false. So let us talk about the language of diagrams, what they can and cannot say. So, as I just said, diagrams are dangerous. Okay, they're also extraordinarily useful. The reason I think that geometry should be a first proof class for students is that we have use of diagrams, and those diagrams allow us, help us as we reason our way through the proofs that we construct. Now, we haven't done proofs yet, and we won't for a little while, but that, as we have said, is the purpose of this class. That's what we do. It is a proof class. Um, and those diagrams are extraordinarily useful, extraordinarily helpful to us in the construction of those proofs. And there is nothing like this in algebra. Your algebra class is not taught as a proof class. Maybe at some point when you're an undergraduate, you'll find that algebra can be done in a proof-based way. But when you do it, you will not have diagrams that will aid you in the construction of your proofs. Nothing that will aid the imagination as you work your way through your proofs. However, in geometry, we do have these diagrams, and they are extraordinarily useful. And that's why it is that I think it's entirely appropriate that geometry is a first proof class, and it historically has been for well over 2,000 years now. However, with that said, we still have to recognize the danger of diagrams, how they can mislead us, how they can allow us, how they can tempt us to make assumptions that we have no right to make. All right, so segments, okay? If you ever see something like what I've pictured here in a diagram, you see the A dot, the B dot, and what appears to be the straight segment between them, you may assume that you have a pair of points connected by a segment. Okay, so that's one of the assumptions that I will allow you to make about a diagram, that if you see something like this, you may assume that you have a line segment. Now, let us consider the case where we have two unconnected points. In the diagram that we just saw, we had two connected points, and we may assume that we have the line segment there. Let us say that we have two unconnected points, just a point somewhere and a point somewhere else with nothing in between them. May we assume that they are collinear? Well, your first thought might be, well, no, unless the diagram has drawn the line from one to the other, we cannot assume that. However, note that we do have the line existence postulate, which tells us that for any pair of points, a line exists that passes through both. So yes, we may assume that if 2 points exist in a diagram or present in a diagram, that a line exists from one to the other. Has it been drawn? If it is not, that is irrelevant. The line existence postulate is still true. It implies the existence of the line even if it is not drawn. So for instance, in the diagram below, are points A and B collinear? That is, does a line exist that passes through them? Absolutely, even though it is not drawn. It is implied by the line existence postulate. And we can draw that line if we want, right? So what I've just drawn a bit poorly, it doesn't even appear to pass through A and B, so I'll fix that with big dots. What I've just pointed out is what the line existence postulate tells us is true, that a line exists. Okay, are points B and C collinear? Well, the line is not drawn, but still it exists, and we can draw it in if we like, and AC as well. Okay, actually, I suppose we end up with a triangle and more as well. But where we have 3 points, then we do have three lines, just like this, which of course will mean that we actually have a triangle. Now, what we'll find later on is that there will be certain situations in which we are allowed to add something to a diagram, and that's actually what we've done here, haven't we? We had 2 points, and we were allowed to add the line from one to the other. So we will call these constructions, and we will talk about them in great detail later on. Now, let us say that we have three or more unconnected points, okay? And we'll see a picture of this in just a moment, but we'll have 3 points. Are they collinear? Answer, if we're not told that they are collinear and we have no information that would allow us to prove that they are collinear, then we absolutely do not know that they are collinear. Perhaps they are not. What I must emphasize here is this, is that we cannot assume that they are collinear based merely upon how they look. Let me say that again. It really is the crucial point of this section. We cannot assume that they are collinear based merely upon how they look. So, for instance, if you were to see a diagram like the one below, you have 3 points x and y and z. Are those 3 points collinear? Well, I will grant you that it looks like they are, but that's all we've got. Okay, we were not told that they are collinear, and we are not given any other information that would allow us to infer that they are collinear. So we must remain agnostic. Now, are x and y collinear? Absolutely. Are y and z collinear? Absolutely. Are x and z collinear? Absolutely, because we know that for any 2 points, a line exists that passes through those two. However, do we know that the line that passes through x and y, does it also pass through z? We do not. Does it look like it will? Well, yes, I suppose, but we do not know that it will. For all we know, it could be a near miss. Okay, so 3 unconnected points, nothing said about the relationship. We cannot assume that they are collinear. Now, how about this diagram, where it looks in the diagram as if they are not collinear? It looks, for instance, that if I connect x to z, y will not lie on that line. Are we allowed then to say that they are not collinear? Absolutely not. Okay, we do not know that they are collinear. We do not know that they are not collinear. Okay, now, of course, it's possible that we were told that they are, or told that they're not, or told something else that would allow us to infer that they are or that they are not. But if the point again is this, is if all we have is the diagram, we do not know one way or the other. Are they collinear? Don't know. Are they non-collinear? Don't know. Now, how about 3 or more connected points? Okay, do we know that they will be collinear? Again, we have to say that unless we're told that they are or not, we don't know. So look at this particular diagram. I have an A and a B and a C. Okay, can I assume that there is a line segment AB? Yep. I told you that you could make that kind of assumption back at the start. Do we know that there's a line segment BC? Yep, I told you could assume that. Do we know that there is a single line that contains all of A and B and C? Well, it looks like A and B and C are collinear. That is, it looks like A, B, and B, C make a straight line, but we do not know that this is true. But for all we know, there's a bit of a bend at B. Okay, so unless we're told that it's straight all the way through from A to B to C, we do not know that it is, okay? And we also do not know that it's not. Now, of course, we could be given, as I've said before, extra information about that diagram, the A and the B and the C, that has been all connected up, that would allow us to infer that we do have one line that includes all of A and B and C. We could be told, for instance, that B is between A and C. I told you before that we only use the word between when our 3 points are collinear. We could be told that one point is the midpoint of the segment created by the other two. That means that they must all lie in a line because that's part of the definition of midpoint. We could be told maybe that they form a straight angle, which just by definition of straight angle means they're all on a line. So yes, we could be given information that would allow us to infer that they are on a line. But if we're not given that information, we simply do not know. So let us say, for instance, in this diagram that goes from A to B to C, that we are told that we have a straight angle, the straight angle ABC. Do all 3 points A, B, and C lie on a line then? Well, yes, we may infer that they do from the definition of straight angle. Now let's talk about how hash marks work. I alluded to this in the previous section, but now let's take this on directly. We know that if 2 segments have the same number of hash marks, they are equal. Do we know that if 2 segments have a different number of hash marks that they're unequal? No, we don't. Okay. Do we know that if 2 segments don't have any hash marks on them at all, either they're equal or unequal? No, absolutely we don't. That's not how hash marks work. Okay. Hash marks can tell us positively that 2 segments are equal in measure, but a different number of hash marks doesn't imply that segments are unequal, and the lack of any hash marks doesn't tell us anything about equality or inequality. So look at the diagram. Okay, so I have this quadrilateral WX, Y, Z. Do remember that if I have something like this W and X with the connection between them, that we can assume that that is a line segment. So I have the line segments W, X, X, Y, Y, Z, and CW connected up. So we do have a quadrilateral. We know that from the diagram. Notice that we also have hash marks as well. And that's really what I want to discuss here. So WX and XY have the same number of hash marks. So the diagram says that they are equal. We know that this is true. Likewise, WZ and ZY have the same number of hash marks, so we know that they are equal. But do we know that WX is not equal to WZ? Okay, absolutely not. Okay, a different number of hash marks does not imply a difference of length. As to the question, is WX equal to WZ? We absolutely do not know, okay, based upon the information given in the diagram. Could they be equal? Yes, absolutely. Could they be unequal? Yes, absolutely, they could. So the point here that I wish to make, and it's one of the most important points about how we understand diagrams, how we use them and potentially misuse them, is that we never assume equality based merely upon appearance. Does it look as if two segments are equal? Perhaps. Does it follow that they are based merely upon the appearance? Absolutely not. Might we be given explicitly information that would allow us to infer that they are equal? Of course, right? I mean, we'll do that very often. But if all we have is the appearance, we can make no assumption at all. We can draw no conclusions. So for instance, look at this quadrilateral. You'll look at it, you'll say, well, that's a square, right? You absolutely do not know, because you do not know the sides are equal, because all you have is the diagram. For all you know, the sides, even though they appear equal, are slightly different. Okay, that's a very real possibility. So how about this one? WXYZ, do we know that it's not, say, a square? That is, do we know that the sides are not equal? No. If all we have is the diagram, okay, the answer is no. Do they look different? Yes, they look different, but we are not allowed to draw conclusions based upon how diagrams look. And I understand that this will bother you, especially this one, right? You will think to yourself, well, if we meant them to be possibly equal, I mean, why did we draw them so obviously unequal? Well, this gets to what the purpose of diagrams is. Okay, the diagrams are simply an aid to the imagination. They're not the basis of the logic of the conclusions that we draw. Okay, so what you must understand about this diagram is that if all we have is this picture, we don't know anything about equality or inequality. So here's another example. So let's say that we have a diagram like the one that you see before. Do we know from the diagram that C is the midpoint? Absolutely not. If all we have is the diagram, we don't know that AC is equal to BC. Indeed, we don't even know that AC and B all form a line. Okay, it could be that there's a slight bend at C so that it's not even straight. So again, you cannot make judgments of this sort based upon the appearance of things. Now, what we've said about appearances and the judgments that you can make based upon them, that is, that you can, that applies to angles as well. So in the diagram, do we know that we have any equal angles? If all we've got is the diagram and nothing's said about it? No, we don't. The appearance of the diagram doesn't tell us anything. Do we know that we have a right angle? Nope, we absolutely don't. We do not. I'll move through this quickly. So do we know that in the diagram below that angle A is right? Nope. Do we know that it's not right? Nope. We just simply do not know. That's a situation in which we will often find ourselves, that we simply cannot determine the answer. Does it look right? Yeah, I'll grant you that. Do we know it's right? Well, if all we have is a diagram, no. So this is just a general rule to keep in mind, okay? We've talked about this in relationship to length and angle measure, but that general point will be true with all kinds of objects throughout the class. Like, for instance, the parallel relation. Let us say that we draw a line in the plane and another line in the plane, and we're not told anything about them. Okay, so we might have, I don't know, something like this. Just I'll draw this very quickly for you. You might see something like that, right? Just here's a line in the plane and another line in the plane. Are they parallel? Are they not parallel? Well, were we told anything about them other than that they're lines? If not, we just don't know. Okay. Whenever we draw a line, of course, we just draw a portion of the line. And is it possible that these two lines would intersect? Yeah, I mean, they look perhaps roughly parallel, but that doesn't mean that they won't finally intersect. Yeah, we just don't know. Okay, we never make conclusions, draw conclusions based upon mere appearances.